Okay, so let's look at this rod of charge or this finite length of charge, which had this form, and now we're going to take it to the length of infinity. And this is again mathematically the same as saying that we are so close to it that r is much, much smaller than L. One of the things we're going to want to do is now actually switch to the linear charge density. Anytime that you actually have an infinite direction of, in this case, 1 or 2, if it's a surface charge, you really do want to use the charge density. The next other thing we need to do is actually rearrange the denominator to take the limit. Right now, we can't just take the limit as L goes to infinity because it looks like everything then that just goes to 0. So that's not helpful. So we need to do some algebra. So what I'm doing, and we can't quite do this yet, we need to actually look for this quantity and then replace that in its place. So what I'm doing to rearrange the denominator is taking this L over 2 and pulling it out front. Now note that it's squared, but it's in a square root, so I'll get an L over 2 up front. But remember that you must divide it by this term as well, and since it's still inside the square root, it would be squared. So all I've done is factored out an L over 2. That leaves 1 here and r squared over L over 2 squared still on the inside. Why is that helpful? Well, now I have a Q over L. Make sure that you don't mess up the algebra for the other steps, but that's at least a start. This Q over L that I showed before becomes my lambda. 2, because it was on the bottom divided out, goes on top, so that's why there's the 2 here. And, right, so that 2 just becomes this 2. R stays on the bottom. And now inside, we can just rearrange a little bit to simplify this down, pull the 2 on top and the L on bottom. So why is this helpful? Look at this term. This is 2r over L. We're taking L to infinity. So if L goes up to infinity, this whole term, right, so this is just L, this whole term is actually going to go to 0. So 1 over the square root of 1 plus 0 is just 1, so this entire term goes to 1. We're then left with everything out front, which still has an r dependence, which is good, and this gives us our answer, that the electric field from an infinite line of charge is twice times the line density divided by r, which is the distance you are from the line. Now in this case, this is the magnitude. Note that it points away. I would call this radial, but it's only radial in a cylindrical sense. It's not radial in a spherical sense. So it's a little hard to use a unit vector to specify this direction in a way that won't be confusing. So it points directly away from the line of charge, and we see that the electric field does get weaker as you get farther away, but it only gets weaker as r, not r squared. So this is quite different than a point charge. Now, infinite lines, as you might be aware, don't really exist in the real world, but there are many cases that we're going to use this. Anytime you have a long wire, and frequently in the description of the problem it will specify it as a long wire, use this form. Anything that's long is effectively infinite. If you are very close to a wire, that means you get to treat it as infinite. So even if you only know that the wire itself is, say, 10 centimeters, but you're a millimeter from it, well, this distance is really small compared to this distance, so we can treat it as infinite. Anytime you are near the center of a wire, you can use this. And again, if you're really, really far away on the center, you still can't. But if you're fairly near the center but still farther away, that's okay to use this. Keep in mind that the derivation when it was a finite line of charge was only for when we are in the center. Do not use this if you want to understand what's happening near the end of a wire. Now the caveat to this is it's very difficult to actually calculate what is happening near the end of a wire. You can do special case, so specific location calculations, but it's really hard to calculate it in general, at least within the scope of this class. So if you have a problem where you're looking at what's called the edge effects or the fringe fields, don't use this. This is the ideal case where you don't see the ends. If you want to see the end, you have to use a different approach.